Rectifying diodes. Rectification is the main purpose or the main usage of the diode. But before we get to that, let's just take a look at the component itself. So here we have a diode which is connected to +5 and +5 volts, and we cannot see any current passing through it. So the arrow on the diode shows the way it should be connected. The current should pass through the diode like that, and the block over here should block the current passing through the other way, except for diodes that actually let current through the other way. So conventionally the current flows from positive to negative, or higher potential to a lower potential. Since these potentials over here are equal, there's no current flowing through here, whether there's a diode between them or not. Also, diode has two leads, anode and the cathode lead. So anode is usually goes to the higher potential and cathode to the lower potential, and usually they are signed as positive and negative lead. So if I change the potentials, there should be some sort of current over here. First of all, let's change the current in here. Let's put it to, let's say 50, or let's say 15 volts. In that case, we can see that there is some current which is actually going from the higher potential to the lower potential. It doesn't block all the current, but basically the current over here is minimal. Also, we might want to look at the current. Let's see, let's add the amp meter between the leads. Show current, apply, okay. And we can see 171 nanoamps passing through. Oh well. Let's change it back to 5 volts. And see what happens. 0 amps. Let's change it to 0 volts. And the simulation crashes. Max current exceeded. Let's see what the max current was. Ooh, it's about a lot of gigaamps. So we need to limit the current. Let's use a resistor for that. Or let's not use a resistor for that. Let's use different potentials that we could have. So let's see. There's no current if we have 5 volt potential difference over here. There's huge current when we have 5 volt potential difference. So let's put it somewhere in between 5 and 0 volts. So let's put it to, let's say, 3 volts difference, or 2 volts that is, and run the simulation. Now we have only 10 gigaamps, which is still a lot. So let's see what would be the reasonable value over here. 4 volts, that is the 1 volt potential difference, and that equals only to 42 amps, which is actually reasonable in some cases. Let's see, 4.5 volts, that's 0.5 volts potential difference, and that actually equals to 2.7 milliamps, which is reasonable, maybe a bit too little. And now to the magic number 4.3 volts. That equals a 0.7 volt difference between the potentials, and that is classically the default value for the diode. It should be forward biased 0.7 volts. For different diodes it's different to get maybe different current passing through, etc. But 0.7 volts is the place we can begin with. So to make it a bit more obvious, I'll change that here to 0 and up here to 0.7 volts and reset the circuit. And there you go. So we can see that the diode lets current through from positive to negative. It doesn't let current through very well from negative to positive, so it only conducts in one direction. And let's take a look at another example. This circuit over here. I have a voltage source that has plus and negative potentials, 5 volts to be exact, and I have a resistor that limits the current, or can be viewed as a circuit that is using the current from our schematic. And let's see, if I have DC over here, then the current is going through the resistor. Now I have 3 switches. The first one lets current through and lets current pass or bypass the diodes, so we can see the current is going through. The second one, or if I open the first one, the current will find the second best path, which is through a diode, which uses about, if we look down here, which uses about volts, which uses about 0.5 to 6 volts. That's close enough to 0.7 that I mentioned before. And so we can see the current passing through here. If I open that switch as well, there's basically no current going through here. Well, if we look at it, we get this 171 nanoamps that is going through here. Now the difference between those two diodes is that this diode is forward biased and that one is reverse biased. So this diode is expecting negative potential on the cathode and positive potential on the anode, which it doesn't receive, so it doesn't conduct. This one does receive it, so it does conducts. What we can do to illustrate this a bit better is use, instead of a DC voltage source, an AC voltage source. So let's edit that to AC, and if we use AC, we can see that, well, actually in this case the plus and minus are irrelevant because they're constantly changing. And we can see that the current is going through one diode and then through another diode. If we take a look at the AC waveform from the voltage source and from the resistor, because whenever we're dealing with AC, it's good to look at the waveforms. And also let's make these a bit more custom. Let's remove the current at this moment. Properties, current, and let's add a negative peak value, which doesn't make a lot of difference in this instance, but it's always good to look at both positive and negative peak values. And let's do the same over here. Show current, negative peak value, okay. And at first glance the waveforms look similar, but if we look at the positive and negative peak values, we can see that over here it's plus minus 5 volts, over here it's plus minus 4.5 volts roughly. And that's because 0.5 volts is or are consumed by the diodes when they are conducting. And if I lift one of, or let's say I'll put the upper switch back in action, we can see the current is going through the path of least resistance in this case, because even the diodes that are forward biased still resist the current more than just the wire over here. So if we bypass the diodes, we can see that the signals are equal. Both have plus minus 5 volts over here. If I lift one of the switches, like this one over here, we can see that the current is passing the resistor only one way. Actually, this is the voltage waveform, but it also applies to the current. We can actually see on the image that the current is passing the resistor only one way. Although the voltage source has plus and minus voltage, we can only see the plus side. So that is the rectification effect that the diode has. Basically, it's a valve. It lets the current go through it only one way and not the other. And now we've converted AC to DC with a bit of loss. On the positive side we've lost 0.5 volts and the whole negative side is lost. So basically we have only half the energy we had before rectification. And if I switch the switches around, we can only get the negative half of the waveform and the positive half is lost. Now, positive and negative are relative conceptions, because we can just flip the circuit and say now negative is positive and the other way around. An easy example in this simulator, if I flip the resistor from one side to another, the previously negative form is now positive. So yeah, I usually say that if the current is passing through counterclockwise, it's negative, and if it's passing through clockwise, it's positive. But that's just what I use. So that's how the diodes work, and that's how they rectify. By the way, this simple schematic over here is called a half-wave rectifier. Basically, if I remove additional stuff, it's a proper half-wave rectifier. A full-wave rectifier would also take the negative side and flip it upside. So we would instead of these zeros over here, we would have another positive side. But that's it for today. Thanks for watching.